Yes, good afternoon, one and all. So I hope that everyone is getting my voice and again screen. The screen also I have shared here. We will start our today's lecture. So before starting the lecture, just we will see. So what we have covered in previous lecture. So in the previous lecture, we have started the second chapter, the block ciphers and again data encryption standard. Now we'll see what we have covered in previous lecture. So what is the meaning of block cipher? Okay. So what are the contents of the block cipher? So you can encrypt the data, the group of the data. Okay, that is called as the one block at a time. So that block contains the number of input characters, and it is used in a broader range of applications. Okay. So the blocks where the data is huge, data is there. So there we are going to use uh, the block cipher applications. And the typical block size is the 64 to 128 bits. Okay. And most algorithms based on a structure are referred to as a Bristol block cipher. Okay. So what is the Bristol block cipher? That also we are going to study in this chapter here. So this is the data encryption standard, that is the DES. As I have given the example that okay, we have the two algorithms. One is called as the SDES, and again another one we have the data encryption standard itself. Okay, so these two algorithms are different one here. So we are learning already. We saw that simplified data encryption standard. Okay, so this is called as the simplified data encryption standard. In short, it is called as the SDES. Okay. So the input of the plain text size is the 8-bit here, and again output or the cipher text block is 8 bits, and again the key we have the 10 bits key here. Again the number of rounds, the two are there. Okay. And again the round keys generated using permutations and left shifts here. Okay. And how we are going to have the encryption, or what are the functions are there in the encryption? So we have the initial permutation, again the round function, again the switch. Okay. And again the decryption also. So the same functions we are having in the decryption here, that is the same as encryption, except round keys used in opposite order. Okay. So here we are going to have the minimum 2 rounds here. So you can increase the number of rounds here, no problem, because if you are going to increase the number of rounds here, then definitely it is going to provide the more and more security here. Okay. So that's why we need to consider the number of rounds here. So this is the algorithm. Okay, yes, DS algorithm is there. So it is divided into the 3 different parts here. So one side we have the encryption and another side we have the decryption here. and in between how the 10-bit key we are going to use for the encryption as well as for the decryption here. Okay, so this is the simplified data encryption standard algorithm is there. So, and this is the separated diagram for SDS key generation. It is there. So, how the 10-bit key is going to accept, and it is going to provide the two keys here. One is the key K1, and again another one is the key K2 here. Okay. So, you should have to remember what is the size of the K1, and again what is the size of the K2 here. So, the K1 size is the 8-bit, and again the K2 size is the 8-bit here. Okay. And so what about the P10 here? So the P10 is called as the permutations on 10 bits, and LS minus 1, and again the LS minus 1. So this is the left shift. So the LS stands for the left shift by 1 bit, and again the LS stands for the left shift by 1. Okay. And again the P8 is the permutations on the 8 bits. And again the LS minus 2, and again the LS minus 2 stands for to the left shift by the 2 bits. Okay. Again the left shift by 2 bits. Again the P8 is called as the permutations on 8 bits here. Okay. So this diagram is for key generation for simplified DS here. Okay. So this is the SDS encryption details. So how the exactly the so this is the internal structure of the diagram here. So how the internally it is going to process the 8-bit plain text for the encryption. So this is the only we have the simplified DES. encryption detail. Okay, but I want to tell you that just you remember what is the input size, what are the different functions they are going to use here. Okay, along with that I will explain how it is going to work here. See, we have the 8-bit plain text here. So this is the 8-bit, and that 8-bit we are going to consider the initial permutations. Okay, and after having the initial permutations, we are going to divide this total 8-bit. That is, the first half is the 4-bit, and again the next half is about the 4 bits are there. So the left 4 bits we are going to take as it is for the next round here, and here we are going to process with only 4 bits here. Okay, and here we have the expansions and again the permutation. So what do we mean by the expansion here? So the expansion is nothing but whatever the 4 bits are there. Okay, so we are going to increase the size of these 4 bits. Okay, instead of the 4 bit we are going to do the 8 bits here. Okay, so output of the expansion and again the permutation function is the 8 bit. Okay, so these 8 bits and again the key k1 8 bits we are having the XOR operation here. Okay, you are going to find here the plus operation. That plus operation is called as the XOR operation. Okay, and along with that, after having the XOR operation, again we are going to divide the two equal parts here. First one is the 4-bit, and again remaining are the 4 bits here. And the next we are going to consider the S0 and again the S1 here. So S0 and again the S1, these are nothing but the S boxes are there. So how the S boxes we are going to implement, how we are going to derive the S boxes, that we are going to consider in case of the data encryption standard algorithm. Okay, so this is the S0, S1, and again this is the S0 and S1 here. Okay, so here you can see that the 0 1 0 0 1 1, again the 1 0. Okay, so the 1 1 1 0 0 1 0 0. Okay, how it is going to, we are going to implement this part, we are going to see into the data encryption standard algorithm. Okay, so why the S boxes we are going to design here? So we need to reduce the size of the characters here. See, for input for the S0 is the 4 bit and output is the only 2 bit. For that purpose, we are going to use the S boxes here. Okay. Again, the next S1 box here. So inside the S1 box, again we are going to take the 4-bit input and we are going to produce the 2 bits here only. So again we are going to have the combination of these 2 and 2 bits here. So it will become as the 4 bits here. So output is the 4 bits are there. Again these 4 bits and again the whatever we are taken as it is the 4 bits. These 4 bits we are going to have the XOR operation here. So output of this XOR operation we are going to consider into the switch function here. So what we are going to do the switch function here. So we are going to swap the left side data to the right side and again from the right side data to the left side here. Okay. Again after having the switch here, again we are going to perform these many operations here. See, whatever these operations we are going to perform here in the first round, the same round once again we are going to have here. Okay. So these are the again same functions we are going to consider for the next round here. So after that we are getting the again the switch function will be there. Again you can increase the one more round here. Okay, it depends on the how much complexity or the security we need to provide. Okay, it depends on that application. If suppose we need to provide the very less security, then we can have the only 1 or 2 round. Suppose we need to increase the security and again the complexity level, then definitely we can go for the number of rounds here. Okay, if we are going to increase the number of rounds, then definitely we are going to increase the complexity level of the algorithm here. Okay, so this is the SDS encryption details. So, and what about the data SDS decryption here? See, this is the one side only the encryption it is there. So how we are going to perform the decryption? So the decryption process is that. So this is the exact reverse process of this one. the same functions are there. Same key K1 is there, K2 is there. Okay, here we have got the 8-bit ciphertext. So the input for the cipher decryption process is that 8-bit ciphertext, and output of this decryption process is 8-bit plain text here. Okay, so these are the yes boxes here. So how the yes boxes we are going to consider? So yes DS and again the DS perform substitutions using yes boxes. Okay, so the yes box considered as a matrix input used to select row or column. Selected element is output. Okay, so the 4-bit input, bit 1, bit 2, bit 3, and again the bit 4. Bit 1, bit 4 spaces row 0, 1, 2, or 3 in decimal. So the bit 2 and bit 3 spaces column, and 2 bit is output here. So suppose that this is the S0, it is there. So in case of the S0 is that we have these are the rows, and again these are the columns here. Okay. So the columns are 0, 1, 2, 3, and again the rows are 0, 1, 2, 3 here. Okay. So in case of the 0, 0 position, we have the 1. Again the 0, 1, we have the 0. 0, 2, we have the 3. 0, 3, we have the 2 here. Again the 1, 0, we have the 3. 1, 1 is the 2. Okay. 1, 2 is the 1. 1, 3 is the 0 here. Okay. Like this one. See what is this one? This is the 0, 1, 0, 0, 1, 1, 1, 0. Okay. So what is the value for 0, 1 here? So the 0, 1 is 0, 1 is 0 here. What is the 0, 0? So the 0, 0 is 1. Means in that way we are going to calculate the SDS or the yes boxes. So this detailed implementation of this yes boxes we are going to cover into the data encryption standard, because in the data encryption standard algorithm we are going to use the only yes boxes there. So the box it is going to play the very important role for increasing the complexity level of the any algorithm here. Okay. So this is one SDS example is there. So how the SDS example? So this is the plain text. The size is the 8-bit. Key is the again 10 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the keys there. And again this is the ciphertext. Okay. So this is about the SDS algorithm. Okay. So in that way we have completed the SDS algorithm. Now we'll see the next part of this one. So what are the block ciphers that we have studied here? We know the block cipher. So along with the block cipher, the one more concept is that the stream ciphers are also there. So what is the stream cipher? So now we got the what is the block? Okay, the block cipher. So we are going to consider the block size. Whatever the input is there, that input we are going to divide into the number of bits here. So that number of bits will become one block here. Okay. So the block ciphers process messages into blocks, each of which is then encrypted or decrypted, like a substitution on very big characters, that is a 64 bits or more. And stream ciphers are it process messages a bit or byte at a time when encryption or decrypting. Okay, so what is the difference between the block cipher and again the stream cipher here? So you remember this one, okay? The block cipher. You may ask for the MCQ question. So the block cipher is nothing but there is a fixed size of the input. Okay, it may be the 64, it may be the 128, or it may be the 56 bit, okay, whatever it may be. But in case of the stream ciphers, it process messages a bit or a byte at a time when encryption or decrypting. Means it is going to consider the stream ciphers. They are going to use 1 bit or a byte. I think you know about the byte. So the byte is the total 8 bits are there. Okay. So these are the called as the stream ciphers here. So the stream ciphers are nothing but it is going to process messages a bit or byte at a time when encrypting or decrypting. Many current ciphers are block ciphers, hence our focus of course. Okay. So the everywhere we are going to use the block ciphers only because we have the huge amount of data here, information it is there. So that is why we need to focus on to the block ciphers here. Okay. So what are the block cipher principles here? So one thing I want to tell you that the block cipher principle is totally based down to the crystal cipher structure. Okay, you know about the crystal cipher structure. So we have remembered in the SDS algorithm. So their SDS algorithm is also totally based on the crystal cipher structure. So what exactly the crystal cipher structure is there that we will see in this slide here. So the block ciphers they are going to work out to the crystal cipher structure. Okay, this is the main principle of block cipher here. So the block ciphers look like an extremely large substitution. Okay, because we have the number of bits here. So would need a table of 2 raised to 64 entries for a 64-bit block. Okay, and arbitrary reversible substitution cipher for a large block size is not practical. If suppose we are going to consider the large block size, then it is very difficult to have the encryption and again the decryption here. Okay. So the most symmetric block ciphers are based on a crystal cipher structure. So the this we'll see that exactly what is the crystal cipher structure it is there. And it is needed since must be able to decrypt cipher text to recover messages efficiently. Okay. So we'll see that what is the crystal cipher structure here. So the Shannon substitution and permutation ciphers here. So what is the Shannon and this? We'll see this one. So in 1949, Shannon. So the Shannon is nothing but is the name of one scientist. Is the very famous scientist there in the computer networks. Okay. You know about you learn in the computer network subject. So in the computer network subject, we have the Shannon formula and again the cloud formula. Okay. So that Shannon is the scientist. He has invented also the in case of the security of the computers here. So in the 1949, Shannon introduced the idea of substitution permutation networks. So the substitute means we are going to replace the characters by character here, and again the permutation means we are going to take the permutations and again the combinations. So the modern substitution transposition product cipher. So these form the basis of modern block ciphers, and substitution permutation networks are based on the two primitives. One is the cryptographic operations we have seen before, that is yes box. Okay, and permutation is the p box, that is called as the transposition. So you remember this one. Yes box is called as the substitution box, and again the p box is called as the permutation box here. So it is going to provide the confusion and again the diffusion of message. So whenever you are going to use the yes box and again the p box in our algorithm, then definitely one more problem is going to arise here. That problem is called as the confusion and again the diffusion. So why the confusion and again the diffusion it is going to arise here? Because we are going to process with the large number of data here at a time. Okay, and that data it is going to provide the two. Suppose the block size is the 64-bit, then definitely it is going to have the number of permutations are 2 raised to 64. Means you can imagine that 2 raised to 64 bit means how much bits will be there. If I am going to take the substitution yes box and again the permutation of p box here. That's why this problem is going to arise. That is called as the confusion and again the diffusion of a message here. So what is the diffusion and confusion here? So it is introduced by Claude Shannon, okay, to thought cryptanalysis based on statistical analysis. So the cryptanalysis. So we learned about the cryptanalysis in the first chapter. So what is the meaning of the cryptanalysis here? So the meaning of the cryptanalysis is that so whatever the output it is there or whatever the cipher text it is there, that cipher text the hacker is going to observe that cipher text and he is going to find out the original message from the cipher text. Okay, that process is called as the cryptanalysis. At that time, that hacker doesn't know that which algorithm is used for the encryption, what the keys are used. The total hacker is unknown to all the things. Then also he is trying to find out the original plain text from the cipher text here. Okay, that process is called as the cryptanalysis here. So assume the attacker has some knowledge of the statistical characteristics of the plain text. Okay. Cipher needs to completely obscure statistical properties of original message and a one-time pad. So the more practically Shannon suggested combining elements to obtain. So the diffusion is that the dissipates statistical structure of a plain text over bulk of cipher text. Okay. And the confusion is that it makes the relationship between cipher text and key as complex as possible. You remember these two definitions here. So it may ask in the MCQ question. So, so the dissipate statistical structure of plain text over bulk of cipher text is called as the diffusion, and it makes relationship between cipher text and the key as complex as possible. So it is called as the confusion here. So now we'll see that what is the Feistel cipher structure here. So the Feistel is the name of that scientist who has invented this Feistel cipher structure. So this is the main principle of block ciphers. Okay, how the block ciphers they are going to have the encryption and again the decryption. So the name of the Feistel is Horst Feistel. Okay, he has devised the Feistel cipher and implements Shannon substitution. So the whatever the yes box has suggested by the Shannons, okay, Claude Shannons, in the Feistel structure, we are going to use the substitution and partitions input block into two halves. Okay. So it process through multiple rounds. We saw that what are the different rounds are there in the SDS. Okay. So based on that, here also we are going to have the multiple rounds here. It's going to perform a substitution on left data half and based on round function of right half and sub key, then have permutation swapping halves. So we'll see the diagram. So there exactly we will see that. So this is the very easy cipher structure is there. Just we should know that what are the different notations. The notations are very important. Okay? So this is the crystal cipher structure is there. So this is the plain text. The size is the 2W bits. The 2W bits is the two words. Okay. The one word size is the 16 bits. So at a time it is going to accept the 32 bits. Okay. See, the first of all, I will tell you that these are the different notations are there. This is the plain text. 2W means 2 words. The size of the one word is the 16 bit. So the total size is the 32 bit. And L0 is the level, that is the left side first level here. And again the R0, it is the right side. Again the next one is the L1. The next one is the R1. Again the next one is the Li. Again the next one is the Ri. So here why you have considered the Li and Ri here, because you can increase the number of rounds here. Whatever the functionality is there in the round one, the same functionality we are going to use into the second round, third round, and again the fourth round here. So the only change is there, the data is only we have the change. Okay. And the remaining functionality of the all the rounds are the same here. Okay. So here in this case, you can see the only we have taken the 3 rounds here. The round 1, round I, and again the round N. So the Crystal has suggested you can take the minimum 16 rounds. Okay, he has made the analysis on this crystal structure, and he suggested that 16 rounds minimum we should take. Then it is going to provide the more security. So the easily it is not vulnerable to get the original plain text using this algorithm. Okay, because it is very difficult to hack the crystal cipher, because in this case we have the multiple rounds are also there and multiple functions are there, different functions. Okay, so it is very difficult to hack the algorithm. That's why the everywhere we are going to use the only block cipher algorithms. Okay. So here in this case you can consider the plain text size is the 2W bits. This is the round one. So what we are going to do here, we are going to divide the plain text into the 2 terms. One is the left half and again the remaining is the right half. Okay. So here we have the substitutions and again the permutations, and this F is there. So inside the F is nothing but the F is called as the complex function here. Okay. So what does the complex function here? See, the key K1 is there. Along with the key K1, we are going to have the XOR operations here. Okay. And again we are going to have the exchange from the R0 to L1 and again from the L0 to R1 here. Okay. How much complexity is increased you can observe here. Okay. And again the same functionality again we are going to apply here. Again the same functionality again we are going to apply into the last round here. And finally we are going to merge with the LN plus RN, so that we will get the secret text of the 2W bits. The one more thing is, remember this one, whatever the input plain text we are going to provide, the same size of the cipher text we are getting here. Okay. In this case, the SDS also you can remember there. The size is the 8-bit plain text. It is going to provide the 8-bit cipher text. So in the crystal structure, 2W bits are the input plain text, 2W bits are the cipher text here. Okay. And along with that, the every round is required here the different key here. Okay. The every round we are going to require the different key here. So this is the key K1, key K2, K3, K4, K5 up to the number of keys we require here. Okay. So this is called as the crystal cipher structure. So I will give the 2 minutes time here. Just take down this diagram in your notebook. Okay. This is a very important algorithm is there of crystal cipher structure here. Okay. I hope that everyone has taken this diagram here. So this is the fiscal zipper, how it is going to work here. The n sequential rounds. What is the n here? So number of rounds we can take here, but minimum 16 rounds we need to take as per the analysis made by Crystal. And substitution on the left half, that is the Li. Apply a round function f, so the f is called as a round function. To the right half, that is the Ri, and take XOR of the output of 1 and again the Li. So the round function is parameterized by the subkey Ki. Okay, so the what is the block size here? Increasing size improves security, but slows the cipher. So if you are going to increase the block size here, then definitely it is going to slow down the execution of the crystal cipher. And the key size is also the increasing size improves security, makes exhaustive key searching harder, but may slower cipher. If you are going to increase the size of the key here, then definitely it is going to slow down our working of cipher. And the number of rounds here, so the increasing number improves the security, but slows cipher. And sub key generation, so the greater complexity can make analysis harder, but slows cipher. And round function is that, so the greater complexity can make analysis harder, but slows cipher. And fast software or encryption and decryption and ease of analysis, so are more recent concerns for practical use and testing here. Okay. So this algorithm is the very easy one. So this is the crystal cipher and again the encryption and again decryption. Okay, how the one and again how the decryption is going to execute. So whatever the previous diagram I shown you, that the same diagram it is there. So the next diagram is about the data encryption standard here. Okay, so here is, so this is the crystal cipher decryption. Okay, so in that way we have covered the crystal cipher structure here. Okay, so I think the time is over here. So I request you all, you kindly put the attendance in the chat box. So I'm going to enable the chat box here. Also, if you are having any doubts or any problems, you can ask me here. And today the attendance is the very less. I have the only 18 students are there. Okay, so do attend the sessions on regular basis. Please put your attendance here.